Hi, this is Ms. Hearn. Let's get started. In this video, we're going to discuss the ratio test and how it applies to how to use it to show convergence and divergence of series. So the ratio test is really helpful with factorial and exponential expressions. It says that a series of non-zero terms will converge absolutely when the limit as n approaches infinity of the ratio of the terms, the absolute value of the ratio of the terms, a sub n plus 1 over a sub n is less than 1. It diverges if that same limit is greater than 1 or equal to infinity, and it's inconclusive when the limit equals 1. So let's look at an example where we use this test. Use the ratio test if possible to determine convergence or divergence of the series. And here we have the series n equals 1 to infinity 1 over n factorial. So to use the ratio test, we have to identify the underlying sequence of a sub n. So we have a sub n equals 1 over n factorial. Okay, now what the ratio test asks you to do is, by the way, that we would, even if they didn't tell us to use the ratio test, since there's a factorial, that's a good guess as to what test to use. But it says to use the limit as n goes to infinity of the ratio of the n plus 1s to the nth terms, absolute value of that. So in this case, what would we have? We'd have the limit as n goes to infinity, and the a sub n plus 1, the n plus first term, is just going to be 1 over n plus 1 factorial. And the a sub n term would be 1 over n factorial. We want the absolute value of that, but remember n is positive. So really, we can drop the absolute values and we can divide that out. We're going to have the limit as n goes to infinity of n factorial over n plus 1 factorial. Now, as we saw in the previous video, when you have a ratio of factorials, you want to think about which is the bigger product. The denominator in this case is bigger because it goes up to a larger factor. So remember, the numerator is just your 1 times 2 times 3 all the way up to n, and the denominator is 1 times 2 times 3. It goes up to n, but then it goes one step further to n plus 1. Another way of saying that is this is the limit as n goes to infinity of n factorial over n factorial times n plus 1, that extra term. So these divide out, leaving 1. So the limit as n goes to infinity of 1 over n plus 1. Since the numerator is a constant and the denominator is getting very large without bound, we know that this is going to go to 0. Since 0 is less than 1, then by the ratio test, we can conclude that the series is absolutely convergent. By the ratio test, the series of the 1 over n factorials converges absolutely. That just means that both the series itself and the series of absolute values would converge. Okay, let's look at another one. So here we have well, it's supposed to be, it looks a little unclear there, the series n equals 1 to infinity of 5 to the n over n to the 4th power. Okay, so when you have exponential expressions, you might try the ratio test, but we're telling you we want to do that in this case. So that means you have to identify your a sub n, which is 5 to the n over n to the 4th, definitely non-zero terms. And we're going to just find the limit as n goes to infinity of the absolute value of the ratio a sub n plus 1 over a sub n. So in this case, that would be the limit as n goes to infinity of 5 to the n plus 1 over n plus 1 to the 4th divided by 5 to the n over n to the 4th. We don't really need the absolute value because if you notice, this expression will always be positive. So I'm going to drop that. This is really 5 to the n plus 1 over n plus 1 to the 4th times n to the 4th over 5 to the n. So we can simplify a bit here. 5 to the n plus 1 divided by 5 to the n is just 5. So we have the limit as n goes to infinity of 5. And then we have n to the 4th over n plus 1 to the 4th. Or another way to write that would be 5 times n over n plus 1 to the 4th. So we're taking the limit as n goes to infinity of this expression. Now this is going to go to 1 because the degrees in the numerator and denominator are the same and the coefficients are 1. So this is going to equal 5 times 1, or 5. And so we can conclude, since this is greater than 1, that this series diverges. So by the ratio test, the series n equals 1 to infinity, 5 to the n over n to the 4th power diverges. So we've seen one where it converged and one where it diverges. Let's look at another one. This is actually an alternating series, -1 to the n plus 1 times n plus 2 over n times n plus 1. But we're being asked to use the ratio test. A lot of times when we see it's an alternating series, we want to use the alternating series test, and we might end up doing that if the ratio test doesn't work. But first, we're supposed to try the ratio test. So what is my a sub n referring to? The whole thing, -1 to the n plus 1, n plus 2 over n times n plus 1. And we want to look for the limit as n goes to infinity of the ratio a sub n plus 1 over a sub n. So what does a sub n plus 1 look like? Absolute value, we're going to have -1 to the n plus 2 times n plus 2, times n plus 3, because we're doing one more, and we're going to have n plus 1 plus 2, in other words, which is n plus 3. And then we're going to have n plus 1 and n plus 2. So this would be the a sub n plus 1 term, and we are dividing that by the a sub n term, which is just the original. Okay, now all the -1 to the n plus 2 and to the n plus 1 is going to do is change the sign. So I'm going to just drop those out, and what's going to be left is all going to be positive, so I don't need the absolute value anymore. So I'll have the limit as n goes to infinity of, now I'm going to flip and multiply, so we have n plus 3 over n plus 1, n plus 2, and we're multiplying by, in the numerator, n times n plus 1, and in the denominator, a factor of n plus 2. We can reduce a little bit, so n plus 1 divides out, and we're left with, in the numerator, we have the limit as n goes to infinity of n squared plus 3n. In the denominator, we have n squared plus 4n plus 4. So highest power dominates, so we're going to look at the coefficients there. Since the powers are equal, it's just going to be 1, which is bad news for the ratio test, because the ratio test is inconclusive when the limit equals 1. Okay, so let's say that this happens to you. You were not asked to use the ratio test, you just decided to use it, and then you get 1. So it's inconclusive, so you would try a different test. So as I mentioned before, this is actually an alternating series, so I'm going to try the alternating series test. So for the alternating series test, we have two conditions that have to hold. If we have an alternating series of the form -1 to the n plus 1 times a sub n, when n goes from 1 to infinity, then we have to check two things. Number one, the limit as n goes to infinity of the a sub n's, does that equal 0? And number two, we need to confirm that the a sub n plus 1's are always less than or equal to the a sub n's. So for the first test, we have the limit as n goes to infinity of the a sub n. In this case is referring to everything except the power of -1. So we would just be looking at n plus 2 over n times n plus 1. So that's the limit as n goes to infinity of n plus 2 over n squared plus n. The higher degree is in the denominator, so this is going to go to 0. So that's good news. It passed the first test. For the second, I tried plugging in, looking at the n plus first term and comparing it to the nth term, and it's not obvious which one is bigger. So instead, in order to show that this is actually a decreasing sequence, I analyzed the function f of x equals x plus 2 over x times x plus 1. So I find the derivative and determine if it's negative, and if it is, then that means we have a decreasing sequence. So I'm going to think of this though as x plus 2 over x squared plus x and use my quotient rule. So f prime of x is going to be the bottom, x squared plus x times the derivative of the top, which is 1, minus the top, which is x plus 2 times the derivative of the bottom, which is 2x plus 1. And that's all going to be over x squared plus 1 plus x squared. And in the numerator, see, this part is actually 2x squared plus 5x plus 2. Over here we have x squared plus x, but we're subtracting, so we're going to have negative x squared minus 4x minus 2. And since the x's are all positive in our function, we're only looking at positive n's in our sequence, so that would be positive x's. This guy up here is always going to be, negative, and then the denominator will always be positive, so we get a negative overall. So what that means is that the function f is decreasing as long as x is less than 0, greater than 0, positive. Okay, so what that means is that we have a non-increasing sequence which satisfies the second condition. So we can say that this series is convergent by the alternating series test. Okay, the series way back up here is a convergence series. Okay, I hope you found this video helpful. If you did, please remember to like it. The next video will be about the root test.